Hello students, now we are taking the second part of the unit 1 where we'll see how to solve the differential equation. Now these differential equations are very important in many physical processes when we try to relate the dependent variable with the independent variable. Normally we get the differential equation. So we should understand how to solve them. However, we are taking only the very basics of the differential equation. So, first of all, what is a differential equation? Differential equation is an equation which involves the derivative of the dependent variable in terms of the independent variable. When we have this differential equation, there are two types of the differential equation. One we call as ordinary, and another one is called partial differential equation. Now the difference between the ordinary differential equation and the partial differential equation is, here we have only one independent variable. But in this case, we have more than one independent variable. Obviously, when you have number of variables, we cannot go directly to the differentiation. We have to take the partial differentiation. So you will find in the partial differential equation the partial derivatives are involved, but we'll restrict ourselves only to the ordinary differential equation. Now there are again two important terms to remember. One is called the order of differential equation. Order of differential equation. When I say the order of differential equation, it is the number which is the highest derivative involved in the differential equation. Suppose there is a differential equation which involves only the first derivative, so its order becomes 1. But if you have equation whose highest order is, say, the second order differential equation, then the order becomes 2 if the second order derivative is involved there. Similarly, there is another important term involved, that is called the degree of differential equation. In a differential equation, first of all find out which is the highest order derivative. The power of it or degree of it is called the degree of the differential equation. The third important term is homogeneous differential equation. Any homogeneous differential equation must have the form dy, the function of, say, x, that is the independent variable, or maybe the dependent variable y, can be written as dx, another function of x and y. If you have this function with the power 1 both sides, then such a differential equation is called homogeneous differential equation. As a first step, we'll understand how to solve the homogeneous first order differential equation. So students, let's take first of all the homogeneous first order differential equation. Now as I told you, an equation, say for example, let me take one example to show it. Suppose I have one differential equation like this. Say this is equals to px qy rx minus, say, sy. This is one form of it. You can have plus minus sign, you can change it. Now this equation is first order differential equation. How can I say this? Because in this the derivative involved is of the order 1. I don't have any second derivative or the third derivative. There is only one order of derivative. So that's why this is the first order differential equation. The next thing is that I have for these functions the power is 1 both in the numerator as well as in the denominator. So this equation becomes a homogeneous differential equation. Now what are the steps involved in the solution of such equation? When we say solution, it means I need a function between y and x, right? Obviously, we have to go for the integration. As you see, we have a derivative. To go to the function, we have to go for the integration. But let's see the steps. First of all, in a first step, we have to separate the variable. Separate variables. That means you take all terms containing, say, dependent variable y on one side and the terms which contain independent variable on the other side. Sometimes it is easy to do it, but sometimes it may not be that easy. So we sometimes require, if need is there, you do the appropriate substitution. You can introduce a new function so that the separation becomes easy for you. Then once you do it, then you integrate both sides. Integrate both sides to get the relation. But since you have done some substitution, as third step, you have to reverse the substitution. Reverse substitution so that you get your function for y in terms of x, right? That is the basically starting dependent and independent variables. Now let's take the second order differential equation. This equation may look like this. The second derivative, it can even have the first derivative and the variable which is dependent variable. Now to handle this type of equations, you have two methods. Since it involves the double derivative, if possible, you can go straight to do the integration twice. But that is possible when a is 0. When this part is missing, you can go for the double derivative easily to get the answer. There is a second method also, and this is called a method complementary function method. Function method. It is basically an operator method where we take the derivative operator d over dx as d. It is a symbol given to the operator. When I write dy by dx, I say that the operator, the derivative operator is operating on y. So if this equation is given to you, you can write the operator equation in this way. D square plus a d plus b operating on y, and that is equals to 0. So once you have this type of the equation, we can solve this quadratic equation, which is the operator equation. For this, sometime we go for the auxiliary equation, aux equation. There what we do is, we take the d as p, and once you write this, this will become p square plus ap plus b, that is equals to 0. This is the auxiliary equation of the differential equation given to you. You treat as a quadratic equation and solve it. If you solve it, this p comes out to be minus b plus minus under root of b square minus 4ac. A is 1 and this is b, divide by 2. So this will give you solution for this quadratic equation. We have here, if two distinct solutions, say my solution is p1 is equals to minus a plus of under root of a square minus 4b divided by 2, and p2 is equals to minus a minus of a square minus 4b divided by 2. My final answer will be for y a constant e to the power p1 into x plus c2 e to the power p2 into x. So this is going to be the solution of the differential equation. In fact, this is a solution, this also is a solution, but we have taken the linear combination of these solutions. The general solution can be taken as the linear combination of all possible solutions for the differential equation. One can further simplify it, but there is a point. If you get the discriminant 0, that means a square minus 4b equals to 0, we are left with only one solution. Let's say this is p. In that case, we write our final answer as c1 plus c2x e to the power px. So this is how the solution is written if you have this particular condition. This method is a convenient method of solving the second order differential equation, but for those cases where we have this as 0. If it is not 0, then we have to go to another part of it, that is called the particular integral. That is not in your course, so we are not discussing it at this stage. Now let's take the first example of the first order differential equation. It is given to us that there is some radioactive material. Initially, the number of the nuclei is n0. With the time, the decay occurs, and at time t, the number is now n. The rate of disintegration, that is dn by dt, is lambda into n, where lambda is the decay constant. Since it is disintegrating, that means the number is continuously decreasing. So that's why there is a negative sign. And we have to find out the expression for n. Let's first of all separate out the variable, the step 1. To separate out the variable, you take the dt on that side and bring the n on the left hand side. You can notice that now the variables are separated. Remember, here n is a dependent variable and t is the independent variable. Now as a second step, step 2, we have to go for the integration. Integrate both sides, and if you do that, this is dn by n is equals to minus lambda dt integral. In order to fix up the limits, sometimes the limits are given and sometimes they don't give limits. But in this case, it is said that at time t equals to 0, the number is n0, and at time t, the number is n. So let's do the definite integration. So this gives me log of n under the limit from n0 to n, and this is equals to minus lambda t. Obviously this is 0, though that minus 0 is there. So we can rewrite this as lambda n minus lambda n0, and that is equals to minus lambda t, or I can write n by n0 as minus lambda t. So taking exponential both sides, which is the inverse function of log, we'll get here n by n0, and in this case we get this as minus lambda t to the power of e. So now we have the expression n0 e to the power minus lambda t. That is the final solution of our differential equation. So students, let's take the second example, and in this example it is given to us that there is a capacitor which is initially charged to a potential V0. Now it is connected to a resistor R. This will make the charge to leak from the positive plate towards the negative plate, creating current through the resistor, that is I. So we can write the voltage across the resistor as I into R. The current is given as minus dq by dt. Once again, why negative sign? Negative sign is indicative of the fact that the charge on the capacitor is continuously decreasing with time. So we can write I, that is the current, is equals to minus d over dt of q, which is equals to C into V. So we write this as current is minus dq by dt. C is constant, so we can take it out. This is I. So once you get the value of I, you put it in this equation. So we write this as minus C into R dV by dt. So this is the differential equation as is required in this question. Now we have to go for its solution. As a first step, we have to separate out the variables. So we can do that by taking dV divided by V, taking the V on this side, and dt on the other side. We have a minus dt divided by CR. Now once the variables are separated out, we have to go for the integration of it, dV by V minus dt by CR. So you integrate both sides. Once again, they have given us the initial voltage. So initial voltage is V0 when the time is 0 here, and finally at any time interval, at time instant t, the voltage is V. So once you do the integration, this will give you log V for the limit from V0 V with a negative sign, that is 1 by CR, and t minus 0. So putting the value here, we'll get log of V minus log of V0 is equals to minus t divided by CR. So log of V divided by V0, by combining the two, we have now minus t divided by CR, or taking the exponential again, both sides, we have V by V0 is equals to e to the power minus t by CR, or we can write V equals to V0 e to the power minus t by CR. So this is the solution of this differential equation. This is the differential equation, and this is the solution of the differential equation. Students, now let's take the third example, and in this example a differential equation is given to us, and this differential equation is dy by dx is equals to y minus x by x. You can notice that in this case it is not directly possible to separate out the variable. You'll find if you just try to take one on the other side, you still will get some mixing of these variables. So we have to go for some substitution. And the substitution we are taking is y is equals to, say, vx. This one has to decide. With experience you will come to know that which appropriate substitution will help you to separate out the variables. Now let's take first of all the right hand side. Now the right hand side with this now will get modified. For y, we'll write vx minus x divided by x. So you can take x common from the numerator, and this is v minus 1 divided by x. So x will be out from the scene, and we get my right hand side as v minus 1. So let me say this is equation 1 and this is equation number 2. Now let's take the left hand side. So we have our substitution as v, y is equals to vx. So let's differentiate this. So if we do this, this will be equals to dy, v as it is dx plus x as it is dy. And we are looking for dy by dx. So divide this by dx, both sides. And if I do that, then I'll get dy by dx is equals to, dx will be out from here, I have v plus, and this is x dv by dx. So now, combining the right and left hand side, we have, say this becomes v plus x dv by dt, dx, sorry, and that is equals to v minus 1. So vv is out from the scene, and we have x dv by dx is equals to minus 1, or we can write dv is equals to minus dx by x. You can notice here that I am able to separate out the variables, but for this I need a substitution. Now this equation is fit for the integration, so integrate both sides. And if I do that, dv is equals to integral of minus dx by x. In this particular case, the initial conditions are not given to us. So we have to use a constant of integration. So if we do that, this integration will give me v, and this will give me minus log of x plus a constant. Now, constant can be taken in any of the form. Choose the form which is suitable to you. Say for example, I choose it as log of c. C is constant, even log of c also is constant. So I can take it in this way. So this v now will become log c divided by x. Now we are at the stage where we have the function v, but as we have substituted for v, so we have to reverse this substitution, and once you reverse the substitution, keeping the v as y by x, so this is now equals to log c by x, so we can write this as y is equals to x log c by x. So this is the solution for the differential equation, where we have to deliberately make certain substitutions to get the separation of variables. Now students, let's take the fourth example. In this, the differential equation is given to us. dy by dx is equals to x plus y divided by x minus y. We have to solve it. But you can notice that I cannot separate out the y and x directly. We have to go for the substitution. And let's try this substitution, vx. If we do this, then first of all, the right hand side, that is x plus y divided by x minus y will take a shape, x plus vx divided by x minus vx. So I can take the x common from numerator as well as from the denominator. I am left with 1 plus v, 1 minus v. Let me take this as equation 1, this equation number 2, and this equation number 3. Now take the left hand side. And when you take the left hand side, this is the first, we have to give the derivative to the equation 2, and that gives me dy is equals to v dx plus, this is x dv, or we can write dv by dx is equals to v plus x dv by dx. Equation number 4. So now combining the equation 3 and 4, we have v plus x dv by dx is equal to 1 plus v 1 minus of v, and that is giving us x dv by dx is equals to 1 plus v 1 minus v minus of v, and if you take the LCM 1 minus v, this makes it 1 plus v minus v, minus and minus will make it plus v square, and this is 1 plus v square divided by 1 minus v. This is how we can write the equation, our differential equation. So now it is fit for the separation of variables. How can we do it? Look, this will become dv. Take this thing on left hand side, 1 by v divided by 1 plus v square, and on the other side we have dx, right, and this x will come in the denominator. So you are able to separate out the variable by appropriate substitution. Now this equation can be integrated. You integrate both sides, and that is 1 minus v divided by 1 plus v square dv is equals to integral of dx by x. Now in this case the initial conditions are not given, so it's not possible for us to put the limits of this integration. So we'll use the constant of integration to cover up the things. So let's first of all go for the integration. Let's separate it out. This becomes dv divided by 1 plus v square minus integral v 1 plus v square dv, and that is equals to integral of dx by x. This is a very standard integral, and we can write its solution as tan inverse of v. This is negative. Now I can take 1 plus v square, and when you differentiate to find out v dv, that will go, and this finally will lead to minus half log of 1 plus v square, and this also will give me log of x plus, let's put the constant of integration as log of c. So now we can easily make out that this is tan inverse of v minus half log 1 plus v square is equal to this is now log x into c. This is the solution of the differential equation which involves v. But since we have the v as y by x, so we have to reverse our substitution. So we write finally this is tan inverse of v by y by x minus half log 1 plus y square by x square, and is equals to log cx. So this is the solution of the differential equation with which we started, that is dy by dx, x plus y and x minus. So let's take the fifth example. In this again a differential equation given to us, dy by dx 2x cube plus y cube divided by 3x y square. We cannot separate out the variable directly, so we have to go for the substitution. Let's take this substitution, y equals to vx. So if we put this substitution here, for dy by dx we get v plus x dv by dx, and here we get 2x cube plus v cube x cube divided by 3x, and y square now becomes v square x square. So we can take the x cube from the denominator and we can remove it from the x cube common in numerator. So this now will give me 2 plus v cube divided by 3 v square. Now take this v on the right hand side and we have x dv by dx is equals to 2 plus v square divided by 3v square minus v. Then this is equals to 3v square 2 plus v square minus 2v cube. This is cube minus 3v cube, and that equals to 2 minus 2v cube divided by 3v square. So we have this equation dx. Now it is possible for me to separate out the variables, and if we do that, this will become 3v square divided by 2 common 1 minus v cube dv, and this equals to dx by x. So this equation now can be integrated, and if you do the integration both sides, we have 3v square divided by 2 1 minus v cube dv and integral of dx by x. Once again, the initial conditions are not given to us, so we'll put a constant of integration in this. Now here, if I try to go directly, it will not be possible. So let's have one substitution here. Let me take let 1 minus v cube as u. This is another variable we are introducing just to get the integration in simpler form. If I do the differentiation of it, I will get this as 3 v square dv, and that is equals to du. Now let's take this integration I, which is equals to 3 by 2 v square divided by 1 minus v cube dv. Now from here you can notice that 3 dv v square can be replaced by minus du, and this is 2u, and obviously this gives me minus half log of u. But since I have done the replacement here and I have to replace it by v first of all, so we write this as minus half log 1 minus v cube. So the integration of the left hand side will have this solution, and on the right hand side this gives me log. So I have minus half log 1 minus v cube is equals to log x plus say log c. I am using this constant of integration as c just to keep the things easy for me, and this now will be equal to half log 1 minus v, and v we have equals to y by x. So I will put this as y cube divided by x cube, and that is equals to log cx. So taking this 2 on that side, we have log 1 minus v cube divided by x cube, and this 2 in the multiplication will give you log c square x square, or I can say 1 minus y square. This is y cube. 1 minus y cube divided by x cube is equals to c square x square. You can treat this c square also as constant. So this is the form. You can further simplify if need is there. Otherwise you can leave at this stage. So students, let's take the sixth example. Sixth example is from the simple harmonic motion. It's given to us that the restoring force acting on a particle which can oscillate in one dimension is directly proportional to the displacement. Since it is a restoring force, so it is always in direction opposite to the displacement. So we can make a statement that the force is equals to a constant K. The negative sign is indicating the restoring nature of the force, and X is the displacement from the mean position. From the Newton's laws of motion, we can write force as d square x over dt square. This equals to minus k x, or we write this as d square x over dt square is equals to minus k by m. K is the force constant and m is the mass of the oscillator. So since k and m, they are constant, so we are taking k by m as omega square, which is also taken as constant. So we have a differential equation d square x over dt square is equals to minus omega square x, or we can write this as d square x over dt square plus omega square x equals to 0. So this is the differential equation for simple harmonic oscillator. We have to solve it. Let's take the first method. First method is based on the direct integration. You might have noticed that since we have the order of derivative is 2, so this is the second order differential equation. We have to integrate it. Since it is a second order differential equation involving the second order derivatives, so we have to integrate it twice, right? So let's first of all restructure this equation. Since velocity is given as dx over dt, this is the velocity. So let me first of all take the second derivative for displacement as dv by dt, and that is equals to minus omega square x. But in this case I have one problem. V is variable, t is variable, x is variable. So we have to make some arrangement so that we'll get only with one dependent variable and another independent variable. To do this, I am multiplying both sides by v minus omega square xv. Now take this dt on that side, so this will become v dv minus omega square x v dt. Since velocity is dx by dt, so obviously dx is equals to v dt. Replacing it here, I'll get an equation in velocity minus omega square x dx. Look at this equation. Now I have two variables, v and x. I can say x is independent variable and v, the velocity, this time is velocity, as dependent variable. Let's go for its integration. Integrating it both sides we have, this will give me v square by 2, and that will give me omega square x square by 2 plus a constant, let me call this as c1. Now multiplying by 2 both sides and readjusting it will give me v square is equals to twice of c1 minus, this 2 will be out from here, minus omega square x square. So what I am doing is, I am taking omega square common. This is 2c1 divided by omega square minus x square. Since c1 is constant, the constant of integration, omega already we have taken as constant. So we can say twice c1 omega square is another constant. Let me call this as a square. We are deliberately taking it as a square. You can take constant with any power, there is no problem. So a square, that is again is constant. So if I do that, the velocity will give me omega square, this is a square minus x square, or you can say v is equals to omega under root of a square minus x square. Although this is the solution for v, but we have to solve it to find out the displacement relation. So next integration we'll do when we replace v as dx by dt omega under root of a square minus x square. Now luckily this equation where we can separate out the variable easily, and this is dx divided by under root of a square minus x square, and that is equals to omega dt. Now this equation is fit for the integration, and if you do that, this will give me integral of dx under root of a square minus x square is equals to omega dt integral. I can integrate this. This will be equals to sine inverse of x by a, and that is equals to omega t plus another constant. Let me put this as phi 0. Phi 0 also is a constant. Now if I take the sign on that side, this will become x by a sine omega t plus phi 0, x equals to a sine omega t plus phi 0. So this is the solution of the differential equation. Here I have just used the direct integration, but since it was a second order differential equation, so I have to integrate it twice, right? Now let's take the second method. Second method uses operator and a complementary function. Let's understand with the help of the example how we can do it. The starting equation was f minus kx for simple harmonic oscillator, which is equals to m d square x over dt square is equals to minus k x, or we can write d square x over dt square is equals to minus k by m x. Since k is constant, m is constant, so k by m is equals to omega square, which is constant. So we can write d square x over dt square plus omega square x, that is equals to 0. So this was our starting equation. We can look at this, that this is the second derivative operating on x, and here we have a constant multiplied with x. So we can do it in an operator equation this way. Take this operator d over dt square, which will give you second derivative with time, plus omega square, and that is to be operated on x, which will give you 0. So we look to this equation in this manner. This is an operator. I can write this as d. This is d over dt, and if it is d square, this is d square over dt square. So this is how the operator equation can be written. So let's get the auxiliary equation. So what I am doing is I am using m for d just to make the thing simple, or you can choose any one of the say expression. Let me choose this time p. So my auxiliary equation for this is going to be p square plus omega square is equals to 0. This is operator equation. So if I take it as a quadratic equation, so I'll find that the p is equals to minus omega square under root, or I can say this is plus minus iota into omega. It means I have two roots now for this auxiliary equation, and that is one is plus I omega and other is minus I omega. So my resultant expression for x to be, remember this is to be taken for time, this is a derivative which is to be taken for time. So x is going to be a constant c1 e to the power 1 root, that is I omega t, plus another constant e to the power minus I omega t. Actually, this is the linear combination of two possible solutions. One can recheck by putting this as a solution back to this equation. You will find this will fit. Once you have two solutions, then their linear combination is also a solution. Now if I expand this, x is equals to c1 cos of omega t plus I sin omega t plus c2 cos omega t minus I sin omega t. This is the expansion for the exponential function. This exponential function can be expanded in this way. So we have x is equals to c1 with cos theta, and this is c2 also with cos theta. So we write c1 plus c2 cos of theta, cos of omega t, and here we have I, that is iota, with c1, and there we have minus of it. So we write this as plus I c1 minus c2 sin of omega t. Since c1 c2 is a constant, c1 minus c2 along with iota also is a constant, so we are replacing it. What we are saying is, let c1 plus c2 is equals to a sine of phi 0 and iota c1 minus c2 is equals to a cos of phi 0. So if I replace it back here, I'll get x equals to a cos of omega t sine phi 0 plus, this is replaced by this a is out, so I have sine omega t cos of phi 0. So if I combine this, I will get the same result as we got by the first method. So this is also one of the effective method of using the complementary function. Since in my equation I have 0 here, so this getting a complementary function part is sufficient. But if you have something here, then we have to use a particular integral also. Of course, this we are not going to study because in our course we have a very homogeneous equation. So this is what the result leads to, x equals to a sine of omega t plus phi 0 for simple harmonic oscillator. So in this seventh example, we are given three differential equations. All of them are of second order, and we are preferring to use the complementary function method to solve all of them. So let's start with the first one. The first equation is d square y over dx square minus y is equals to 0. So very first step is to write the operator equation. So once again we have d by dx is equals to d. So I can write this as d square minus 1 y equals to 0 is my operator equation. So once again I am choosing for the auxiliary equation d equals to p. So that quadratic equation now will take a shape p square minus 1 is equals to 0. So when we solve for p is equals to 1 under root with plus minus sign. So I have two solutions, one is plus 1 and other is minus 1. So writing the final solution, that is equals to y, the constant e to the power 1 plus 1x plus c2 e to the power minus 1x. That means y is equals to c1 e to the power x plus c2 e to the power minus x is the solution for the first equation. Now take the second equation. The second equation is d square y over dx square minus 3 dy by dx plus 2y, and that is equals to 0. So once again, get first of all the operator equation. The operator equation here will be d square minus 3d plus 2 operated on y, and that is equals to 0. So the auxiliary equation where I am replacing d by p, the quadratic equation will be p square minus 3p plus 2 is equals to 0. Now this can be solved, is a quadratic equation. So p square minus 3p plus 2, you can write this as p square minus 2p minus p plus 2 equals to 0. So p common, p minus 2 minus 1, p minus 2 equals to 0, giving me p equals to 1 and p equals to 2. So we can write the final answer for our differential equation, that is equals to C1 e to the power 1x plus C2 e to the power 2x. This is the solution for the equation number. Now let's take the third equation. Third equation is second derivative of y with respect to x plus 4 of first derivative plus 4y is equals to 0. Let's first of all get the operator equation. Operator equation is d square plus 4d plus 4 y is equals to 0. So from the auxiliary equation where I am replacing d by p, so this is p square plus 4p plus 4, that is equals to 0. Now if we go for the p, this is minus 4 plus minus under root of 4 square 16 minus 4ac, that is equals to 16 divided by 2a. So we find that in this particular case we are getting only one solution, one real solution, and that is minus 2. Obviously, when you have a differential equation of the second order where we are finally getting the one real solution, of course this part will go. So we treat this as if we have two solutions, minus 2 and minus 2. So when you have the similar solution for the quadratic equation, there we have one special form of the presentation of the result, that is equals to C1 plus C2x e to the power minus 2x. That is how we have to write the answer for the differential equation of this form. Now let's take the 8th example. In this it is given that there is a capacitor which has a maximum charge, say Q0, having a value C, is now connected to an inductor L. Now what happens when you connect it like this? Then charge will start flowing through the inductor and inductor start producing the EMF, that is what we call as an induced EMF. So if I represent the potential drop across C, that means capacitor VC, and about inductor VL, so according to the Kirchhoff rule, voltage rule, the sum must be 0 when the loop is completed. Now what is VC? Say at time t, the charge on the capacitor is Q divided by C, that is the voltage difference across the plates of the capacitor. For inductor, this is minus dLi by dt. Induced EMF is represented as minus LdI by dt. This negative sign is because of the Lenge's law. But I, the current, is minus dq by dt, which means that as current develops, the charge on the capacitor start decreasing. So that's why this negative sign is there. So if I put it back, so this becomes Q by C plus L d square Q over dt square, and that is equals to 0. So this is the required differential equation for this type of the circuit arrangement. Now let's solve it. This is d square Q over dt square minus Q by C. So this is d square Q over dt square minus Q divided by L C. So this is the form which is similar to the form we have seen for the simple harmonic motion. Obviously the charge will oscillate in this type of a circuit, assuming the inductor to be pure inductor and capacitor to be the pure capacitor. So let's simplify it by writing the operator equation, which is d square plus 1 by LC, and that operates on charge Q to give you 0. So what we now can do is, we can treat d as a variable p. So the auxiliary equation now will be 1 plus LC, that is equals to 0. So p comes out to be the plus minus iota of 1 by under root of LC. So since we have to now the solution here, so what we can do is, we can write our final equation as C1 e to the power I 1 by LC t, that is in time, plus C2 e to the power minus I 1 by under root of LC into t. So this is the required solution for the equation. If you simply expand it and try to simplify, you will get this is equals to Q equals to Q0 sine of 1 by under root of LC into t plus phi of 0, as we have done in the case of the simple harmonic motion. We can write omega as under root of 1 by under root of LC. So the equation can even be written as Q equals to Q0 sine omega t plus of phi 0. The similar result as we have seen in the case of simple harmonic. Now let's take the 9th example, and this is on damped oscillator. Damped oscillator experiences two forces. One is a restoring force, which will try to bring the body back to its main position, and other is a frictional force, and this frictional force is directly proportional to the velocity of the body. So if we write down the equation of such an oscillator, we can write it like this: F is equals to minus kx and minus b dx by dt, that is the velocity. So taking the force from the Newton's second law, you can write this as m dx over dt square, that is acceleration multiplied by mass, plus kx plus b dx over dt, that is equals to 0. So dividing by m the entire equation, we have d square x over dt square plus b by m dx by dt plus k by m x is equals to 0. Since b the damping constant, m mass, and the force constant, they are constants. So let b by m is taken as 2 gamma and k by m is equals to omega 0 square, because these are constants. So we have taken these constants in a very special manner just to keep the Mathematics simple. So if I replace it here, so my differential equation will now take the shape dx over dt square plus twice of gamma dx by dt plus omega 0 square x, that is 0. So writing it in the operator form, this can be written as d square plus 2 gamma d plus omega 0 square operated on x, that is equals to 0. So from here we can generate the auxiliary equation taking d as p, and once you get this becomes p square plus twice gamma p plus omega 0 square is equals to 0. This is the quadratic equation and we can solve it. This is minus 2 of gamma plus minus, this is coefficient is 1 minus 4 b, this is 2 gamma, b square is 4 gamma square minus 4a, and c is omega 0 square divided by 2. So p comes out to be minus gamma plus minus, this 4 and 4 can be taken out, and this is equals to gamma square minus omega 0 square. So there are two solutions now. One is for p minus gamma plus of under root of gamma square minus omega 0. Another one is minus gamma minus of gamma square minus omega 0 square. So we can write our final answer for the displacement x as c1 e to the power minus gamma plus under root of gamma square minus omega 0 square t plus c2 e to the power minus gamma square minus omega 0 square into t. So this is the solution for the damped oscillator. One can further elaborate it, expanding the e function and collecting the remaining terms to simplify it, but this is the desired solution for this differential equation.